Hello everyone, welcome to the second part of a series of lectures and tutorials about hierarchical multiple regression. In the previous episode, I reintroduced what hierarchical multiple regression is and what are the typical situations wherein you can use or utilize hierarchical multiple regression. For today, I will talk about how to run hierarchical multiple regression using an open source software called JASP. Before we continue, I'm inviting everyone to kindly subscribe to my YouTube channel. More than 90% of the people who are watching these tutorials are not subscribed, so I would really appreciate it if you can help me, help the channel by subscribing. From the previous video, we showed this particular model that we want to test. So this model would like to test what are the social predictors of mathematics proficiency. Specifically, these social predictors can be clustered or categorized as risk factors, specifically bullying and school safety risk. And then there's also protective factors, particularly belongingness, disciplinary climate, and teacher support. But prior to testing whether these variables predict mathematics proficiency, we specifically want to know whether these predictors account for mathematics proficiency on top of what our control variables, sex, and socioeconomic status can explain. This is our data set. So we have a number of variables here. By the way, this is JASP. So JASP, as what I've said, is an open source software. It can run several analyses from descriptives, t-test, ANOVA, mixed models, regression, even machine learning, network analysis. It even has process macro. It can even run basic structural equations modeling. But for today, we'll focus on how to run hierarchical multiple regression. So as you can see, our data set includes gender. This is a dichotomous variable. I also coded gender as 0 and 1. So female is female coded as 0, male coded as 1. And then we also have a measure of age, sense of belongingness, exposure to bullying, school safety risk, disciplinary climate, teacher support, and our measure of economic, social, and cultural status, and then our measure of math proficiency. Before we test the actual hierarchical multiple regression, let's perform some basic preliminary analysis, particularly our descriptives. So to do that, we simply click on descriptives, and then we choose descriptive statistics, and then we want to enter the variables that we want to describe. So that would be math proficiency, and then our predictor variables beginning with the risk factors. So bullying, exposure to bullying, and then school safety risk. And then we also want to add now our protective factors, sense of belongingness, disciplinary climate, teacher support. And then we add our control variables, sex, and then economic, social, and cultural status. So this is our result. To have a better view of the result, I suggest that you choose transpose the descriptive table. That way, the columns would be the statistics and the rows would be the variables. And then by default, what is showing here are the valid responses. So this suggests that we have 6,510 participants. There are 0 missing values. These are the averages or the means. And then we have the standard deviation. We have the minimum and then the maximum. If you're interested in other statistics, you can select what you want from these options. So if you want a measure of the median, so you can check that, and then it will show a measure of the median. But for purposes of this demonstration, what we're only interested in really is the mean and the standard deviation. So I'm gonna uncheck the other statistics, and I will simply retain the mean and the standard deviation. Now, please take note that this will not make sense. No? So average sex and standard deviation for sex, of course, that wouldn't apply. So you should be ignoring these values. Of course, we cannot compute, the mean and standard deviation for sex. But if what you want is the frequency distribution, or if you want to know how many are males, how many are females, we can enter the variable gender, and this is a categorical variable, specifically the one which is not coded. Naturally, like what I said, it will not compute for the mean and the standard deviation. But for categorical variables like this, you can select tables and check on frequency tables. And when you do, a result will appear that informs us that there are 3,325 females and 3,185 males, and then their corresponding percentages. So these information will be helpful, specifically when you want to report about the description of the sample. And while we're at it, let's also include age in the descriptives so that we know what the average age is, even if age is not a control variable. So the average age here is 15.74 years old with a standard deviation of 0.29 years. So after we have performed our basic descriptive analysis, let's run some preliminary correlations just to check if our variables are correlated with one another. We select regression, and then under regression, specifically under classical statistics, we choose correlation, and then we enter our variables. Typically, I enter first the outcome variable, followed by the predictor variables. Just as in the previous analysis, let's begin with the risk factors. So being bullied, school safety risk, followed by the protective factors, belongingness, discipline, teacher support. And then lastly, let's enter our control variables. So the sex, particularly the one that is coded. If you enter gender, it will not analyze. And then our measure of economic, social, and cultural status. I could also enter age. However, this particular population is very homogeneous. So these are basically 15 and 16-year-old students. So there's no point really in controlling for age or entering age in the correlation analysis. And then specifically the kind of correlation that we're doing here is Pearson R correlation, since these are scores. And even if we have a dichotomous variable, sex, Pearson R correlation can actually accommodate such a variable. So this is our result. So we can see that the result is in matrix form. For each pairing of the variables, for example, exposure to bullying and math proficiency, the results of their correlation can be seen in these two cells. So the first value is the correlation coefficient. So the correlation coefficient is negative 0.374. So that means to say that math proficiency is negatively correlated to bullying exposure, and that this coefficient is significant because the p-value is less than 0.001. And the rest of the correlation matrix can be seen here. Now to simplify this, what we can do is to uncheck report significance, and by doing so, the p-values are removed from the table. And then to identify which of these correlation coefficients are significant, we simply click on flag significant correlations. And when we do, the correlation coefficients will now have asterisks, particularly correlation coefficients that are significant. So among these coefficients, negative 0.013 is not significant, negative 0.006 is not significant. So those are specifically the relationship between sense of belongingness and economic, social, and cultural status, as well as discipline and ESCS. So there is no significant correlation among those variables. And then the asterisks mean specific things. So if there are 3 asterisks, that means to say that the coefficient is significant at 0.001. If there are 2 asterisks, the coefficient is significant at 0.01. If there's only 1 asterisk, such as this, then this coefficient is significant at 0.05. Now, you will notice that there is a specific order or style. This is a personal style of mine. So in entering the variables, the sequence would be the outcome variable followed by the predictor variables. If there's a specific order for the predictor variables, then follow that, and then last would be the control variables. So what do we see here now? As expected, our risk factors, being bullied and school safety risk, are both negatively correlated with math proficiency or math achievement, whereas our protective factors, belongingness, discipline, and teacher support, are all positively correlated with math achievement. Sex is negatively correlated, but what does that mean? We can't really say that sex is negatively correlated. This means that females tend to perform better in math. And why do we say that? Because if you remember, female is coded as 0, and while male is coded as 1. So that means to say that the lower the value, which represents female, 0, the higher the math performance. Hence, the coefficient is negative. And the higher the value, what is the higher value? 1, male, the lower the performance. So this suggests that females tend to perform better in math compared to males. And then finally, as expected also, socioeconomic status is positively associated with mathematics proficiency. So that means to say that students who are higher in socioeconomic status tend to perform better in math compared to their low socioeconomic status counterparts. Finally, let's now run our hierarchical multiple regression. So to do that, let's click on the regression again. Then let's select linear regression. Let us enter our dependent variable or our outcome variable, which is mathematics proficiency. The method is enter. Then let's enter our covariates or our predictor variables, beginning with our control variables. So sex and socioeconomic status. Now, why sex and socioeconomic status? Because these are our control variables. These are the first two variables in our hierarchical blocks or hierarchical steps. So that's why I'm entering it first, followed by risk factors, because those are the variables that we enter for the second step. So those are bullying experiences, school safety risk, and then lastly, our protective factors, sense of belongingness, disciplinary climate, and teacher support. Now, previously, JASP can only handle a two-step hierarchical regression analysis. That's why I don't really use JASP in teaching hierarchical regression. But now, you can actually perform multiple steps. So, the default is two models, model 0, model 1. But I want to replace that as model 1 and model 2. Model 1, of course, is sex and economic, social, and cultural status. So let's enter that for model 1. You will notice that as I enter, it's kind of removed from model 2. If I enter SES, see, the colors have been muted as well. So far what we have is a two-step hierarchical regression, but let's add another step. So let's add another model, and let's call this as model 3. So for model 2 specifically, this is only bullying experiences in school safety risk. So let's remove belongingness, discipline, and teacher support, because those are for step 3. So let's enter those. So belongingness, disciplinary climate, and teacher support. So those are the last 3. And if you notice, if you want to add another step, you can do so. Model 4, model 5, model. So it seems that you can add as many models as you want, but for the meantime, this is only a 3-step hierarchical regression analysis. So these are the results. I'll try to explain what these results mean, what to look for. But for the meantime, let's see if there are other things that we need. So let's try to report the R-squared change. I briefly explained what the change in R-squared is in the previous lecture. So if you haven't seen that, I suggest that you check it first. And then the F ratio for the change in R-squared. Considering that this is a multiple regression analysis, let's check for collinearity by checking on the tolerance and the VIF. Although looking at the correlation coefficients, coefficients are very modest, so we don't suspect any multicollinearity concerns. But let's check nevertheless. What we want here is a tolerance that does not exceed 1 and a VIF that does not exceed 3. So it seems that we are safe, for collinearity. So no large values here. So we're just doing that to check. So we can uncheck that already after briefly checking. What else? So that's it. So what do these values mean? So you will notice that these results come in threes. We've specified that we have 3 steps or 3 models in the results that is referred to as M0, M1, and M2. So these are our 3 steps. So for step 1, let's have a review. Our outcome variable is mathematics proficiency. Our predictors are sex and socioeconomic status. For model 2, we have the same outcome variable, but this time our predictors are sex, ESCS, bullying experiences, and school safety risk. So we have 4 predictors. And then for model 3, we added 3 more. So we have 7 predictors now. We have the same outcome variable, mathematics proficiency, but our predictors now are sex, ESCS, bullying experiences, school safety risk, sense of belongingness, disciplinary climate, and teacher support. So these are the results. So for each of those models that I have identified a while ago, there are measures of R, R squared, adjusted R squared, change in R squared, and then the corresponding F ratio for the change in R squared. We also have corresponding ANOVAs for the R squared. Okay, so briefly, what are these again? So R squared refers to the multiple correlation coefficient. This measures the correlation of the variables as a collective. So sex and socioeconomic status. For model 2, sex, socioeconomic status, bullying, and school safety risk. For model 3, all of the 7 variables. What are their correlation as a whole to math proficiency? So as you would expect, there is an increasing correlation because we have more and more variables. But that's not really very relevant. What is relevant is the variance explained. So R squared. So when you multiply 0.262 by itself, you get 0.069. So this is basically the square of your multiple correlation coefficient. So these values, as what I've said, are measures of variance explained. So what is it again? So our outcome variable is mathematics proficiency. Mathematics proficiency vary, right? Imagine 100 students. They would have different levels of mathematics proficiency. If they have different levels of mathematics proficiency, that means to say that there is variation. Now, what are the reasons why some students have higher mathematics proficiency while other students have lower mathematics proficiency? So you can imagine a list of possible reasons why you might include variables such as intelligence, nutrition, so forth and so on. And if we imagine all of the possible variables, theoretically, these variables will predict 100% of the variation in mathematics proficiency. But the question is, how much, for example, out of 100%, can the variation in sex and socioeconomic status can account for? And the answer is in this particular value. So to better appreciate this, you can translate this into percentage. So the percentage form of 0.069 is 6.9%. So that means to say that 6.9% of the variation in mathematics proficiency can be accounted for collectively by sex and socioeconomic status. Of course, this is only an estimate. We also have to ask, is this significant? Is 6.9% variance explained significant? We can check the ANOVA result here. So with a p-value of less than 0.01 of this F ratio, this is our evidence that this is significant. Now, what about model 2? Model 2 is sex, socioeconomic status, bullying experiences, and school safety risk. So those 4 predictor variables can account for this much variance in mathematics proficiency, or in percentage, that is 22.8%. Is 22.8%? Well, obviously it is. If 6.9% is significant, then the much larger value should also be significant. And this is our evidence for its significance. Now, the question is, but what about bullying and school safety risk only, not including what is already accounted for by sex and socioeconomic status? So what we do simply is to subtract this r squared from this r squared. And that is what we refer to as the r squared change. And if you subtract 0.069 from 0.228, this is what you will get. So this is the additional variance explained by adding bullying experiences and school safety risk. So if sex and socioeconomic status can explain 6.9% of the variation in mathematics proficiency, bullying and school safety risk, their variation can explain an additional 15.9% of the variation in mathematics proficiency. Is this significant? This will tell us if it's significant. So the p-value is less than 0.001. So that suggests that this is a significant change in r squared. And then finally, what about the last model? What if we add the 3 protective factors: belongingness, discipline? So we now have 7 predictors. The variance explained becomes even larger at 0.275 or 27.5% variance of mathematics proficiency explained. Is this significant? Yes, it is. But the question is, how much can the last 3 predictors, can the protective factors explain? So same thing, we subtract this from this. And what do we get? The r squared change. So the 3 protective factors explains an additional 4.7% in the variation in mathematics proficiency. So that's how you interpret these results. By the way, is 4.7%, is this significant? Again, let's check on the corresponding ANOVA for that. Yes, it is. And at the bottom part of the result would be your individual contributions. Now, what is meaningful here, I suppose, is the final model. This model, I think, is what is most significant, because in this last model, we're now examining if these predictors uniquely contribute to math proficiency, controlling for the other predictor variables. So these are what we refer to as our unstandardized regression coefficient. The statistical notation for this is the letter B, and then this is the corresponding standard error for these unstandardized regression coefficients. They're unstandardized because these values are measured based on the raw measures. So a traditional way of appreciating these values, this is the change in math proficiency for every 1 unit increase in the predictor variable. So if bullying increases by 1 unit, then it's predicted that there will be a negative 11.932 unit of math proficiency decrease. If there is a 1 point increase in belongingness, then it's predicted that there will be an increase also of 12.559 in math proficiency. But we're not really very particular about this, no, because we are psychologists and what we're talking about are really arbitrary values. Anyway, so those are unstandardized regression coefficients, and then these are our standardized regression coefficients. So you can take this as kind of the z-score counterpart, kind of. So what we said is that these values are based on the raw score, how the scores are measured. But if you convert all of these scales into the same scale, then these are the standardized values. And using these values, the contribution of these variables become comparable now. So I can say, for example, that it seems, at least numerically, bullying seems to have more weight in influencing mathematics proficiency compared to, let's say, for example, teacher support, which is a lower value. And then to know if these are significant contributions, the question is, are these values significantly different from 0? Because 0 means that they do not contribute to mathematics proficiency. But are they significantly lower or higher than 0? And thus, a t-test is performed comparing these standardized regression coefficients to 0. These are your t-values. And these are the probability that these values being different from 0 is a product of chance. And considering that the probabilities are very low, therefore, low probabilities, particularly less than 0.05, 0.01, 0.001, depending on your alpha, is taken as an evidence that these standardized regression coefficients are significant. So judging from the results, or judging from what we have here, it seems that all of our variables, control variables, and our actual hypothesized variables, predictor variables, are all significantly contributing to mathematics proficiency. Particularly, females tend to perform better in math compared to males. Higher economic, social, and cultural status predicts higher math proficiency. Higher bullying experiences predicts lower math proficiency. Higher perception of school safety risk predicts lower math proficiency. Higher sense of belongingness predicts higher math proficiency. Higher disciplinary climate predicts higher math proficiency. Higher teacher support predicts higher math proficiency. Apologies, I should have been referring to the standardized regression coefficients. Why do I sometimes say that, lower this leads to higher math proficiency? I'm basing, of course, on the valences, if it's negative or positive. All right, so that is how you run hierarchical multiple regression in JASP. If you have any questions, you can post them in the comment section and I'll be happy to answer them if I can. So again, if you learned something from this tutorial, I'm inviting everyone to please subscribe to my channel and help me grow this channel. Thank you. I'll see you in the next video. In the next video, we'll talk about how to translate these raw JASP results into APA formatted tables. See you.